Hi everyone, I'm John Henderson, an application scientist at Agilent Technologies, and I'm here with Ron Majors, senior scientist. Today we're going to continue with another LC troubleshooting topic. In this section, we'll talk about pressure in your HPLC instrument. Excessive back pressure can cause problems for your column and for your chromatographic results. Ron?
This is really an important topic and one of those common problems we see, changing column pressure. Column pressure change is a symptom of something that is going on in your system or in your column. When micron-sized particles are packed into a column and liquid is pushed through these particles by your pump, there's a lot of resistance. It's this resistance to flow that causes back pressure.
You know, Ron, there are more than a few factors that contribute to system pressure.
Yes, John, there are actually 5. Let's look at the pressure equation to quickly understand what affects column back pressure. First of all, there's solvent viscosity. The more viscous the solvent, the more force it takes to push the liquid through the packed bed, and therefore your pressure will rise. For example, if you're using acetonitrile as your organic solvent in reverse phase HPLC, and you change to isopropanol, which is more viscous, your pressure will rise directly in proportion to the increase in viscosity. If you're familiar with the water methanol mobile phase, popular in gradient elution, the actual viscosity of the mixed solvent changes with composition. Let's look at this graph. Here, one can see with 100% water, the viscosity, and of course the pressure, is fairly low. But as the amount of methanols increase, the actual viscosity rises and reaches a maximum around 45% methanol. Adding more methanol will cause a decrease in pressure until at 100% methanol, the pressure is actually lower than it was to begin with. This change in pressure is due to a change in viscosity during gradient elution. The pressure increase could cause a problem if you're working at a high pressure already, and the increase due to this viscosity may cause an overpressure in your system, shutting it down. The second factor that affects pressure is flow rate. The faster the pump pushes mobile phase through the column, the higher the pressure resistance due to flow rate. The third factor, L, is the column length. The longer the column, the more pressure it's going to take to push mobile phase liquid through it. Pressure doubles when the column length doubles. Probably one of the most poorly understood factors in the pressure equation is the particle diameter, because it's inversely proportional to the particle diameter squared. Thus, when the particle size is reduced by 1/2, pressure rises by a factor of 4, or 2 squared. With the new sub-2 micron particles, pressure may become quite high, and thus entire new technology has arisen called ultra-high pressure LC, or UHPLC. You'll notice in the equation that the column radius is inversely proportional. At a constant flow rate, if you decrease the column diameter from 4.6 millimeter to 2.1 millimeter, pressure increases 5 times. Note that the column permeability is a constant and dependent on the type of bed one is dealing with. Now that you understand what causes pressure drop in a chromatographic column, let's look at some of the common problems you might encounter that will cause the pressure to change. We could actually have 3 types of pressure problems. The most common problem is very high pressure. Very seldom does the pressure of the column make a dramatic change. It's usually a very gradual thing. The second area is low pressure. There are cases where the pressure can drop on your column instead of increasing. A lower pressure is most often the result of a system leak or a loss in pump prime. The third area is fluctuating pressure or constantly changing pressure. Fluctuating pressure is often a result of check valve sticking or malfunctioning. Since pressure increase is the most often occurrence, we'll confine our discussions to the first case.
Okay, let's first look at HPLC system causes of pressure. Any obstruction in your flow path, all the way from the mobile phase inlet to the mobile phase outlet, can be a restriction. To cut down on extra column band broadening, we often use very small internal diameter tubing in HPLC. So the tubing itself can cause a back pressure. In fact, some very high efficiency columns available now are optimized with very narrow tubing like the 0.12 millimeter ID tubing. There is a system back pressure associated with all this tubing from the pump to the detector, even without a column being present. So there's some contribution to the total system pressure from the hardware.
Of course, anytime something lodges inside one of these small tubes, a piece of dust, a burr of metal, or something like that, this may change the pressure in your system. So things like tubing, fittings, flow cells, inline fillers, and other small system volume elements may have obstructions. and this may affect your pressure. The pressure will usually rise if you have any of these restrictions in those areas. If the restriction occurs past the detector, this could be disastrous because the flow cell cannot take very high pressures and will generally leak or even break under the strain.
So let's talk about how we go about troubleshooting pressure issues. Often, finding the source of high pressure can be a time-consuming part of troubleshooting.
Yes, John, that's true. So the more you know about how your flow path is constructed, the more quickly you can discover the source of pressure problems. Let's assume we've experienced an overpressure condition which shuts down our chromatograph. To solve this problem, we must locate the source of restriction. On newer instruments, including the 1290 Infinity LC, the software does not allow you to exceed the instrument pressure limits and will automatically adjust flow to reduce pressure. In this case, you want to be aware of the normal pressure in your method and watch for it to start creeping up.
To determine if the system or the column is the source of the pressure buildup or restriction, the easiest way to begin the diagnosis is to remove the column from the system. If the pressure immediately decreases, then we can probably be assured that the column is the culprit.
If a guard column or an inline filter is present, we should also disconnect them one at a time to see if the blockage is occurring in one of these components. If the system pressure stays high when the column or guard column or inline filter is removed, then we must work our way upstream of the column to figure out where the restriction is located. So the next possible upstream blockage could occur in the piece of capillary tubing connecting the injector to the column. By disconnecting this capillary, we can quickly find out if the blockage occurred there. Still, if the pressure remains high, once we remove that fitting, we must continue to work further upstream, removing one component at a time until the clog is found. Once located, the culprit must be replaced in order to solve the back pressure problem. We will also consider what might happen inside your HPLC column. On screen, I'm showing a diagram of a column. As you can see, there are frits on both ends of the column, both an inlet frit and an outlet frit. You have infittings on both ends, and you have packing inside the column. All these areas can be places where material may build up that restrict the flows. For example, on the inlet side, which is especially vulnerable, any small particulates, even micron size, that can come from your sample, from your mobile phase, or from your solvents could lodge in the frit. Here's a photo that shows a clean frit and a clogged frit for comparison. So let's first talk about blockage of the inlet frit, which is probably the most common cause of increased pressure. The frits are small, porous stainless steel discs that have porosity usually in the range of about 2 micron or 1 micron, half a micron. So these are very fine filters on their own right. And of course, they can be blocked by particulates that happen to come from the various sources.
These types of pressure increases are usually very gradual. In other words, they don't occur within minutes unless something very serious is wrong with your mobile phase or sample.
That's right, John. These should happen over a period of a few days, weeks, even months. That's why we recommend to keep a logbook where pressure is recorded over a period of time. So pressure buildup at the head of the column is one area that we'll address. We can see the pressure information on every chromatogram on our chem station.
So Ron, what are some of the sources of these particulates?
Well, some of the particulates could actually be in the sample. For example, if you haven't filtered your river water sample, it could have silt or microbes in it. This silt could build up on your inlet frit.
Another source could be the wearing of your injector or septa particles from your vial cap.
Your pump seals are yet another source of particulate generation. As your pump is used month in and month out, eventually you have to replace your seals. Also, during the process of seal wear, very small fragments of graphite-filled Teflon, or whatever seal material your pump happens to use, could find its way through your flow lines, your tubing, your pulse dampener, etc., and lodge in your column inlet frit.
The mobile phase can be a source of contaminants too. For example, buffer preparation involves many manual transfer steps. In each of these steps, possible introduction of particles can occur.
Let's assume that the column is the source of contamination by particulates that have lodged on the inlet frit. How do we get rid of these particulates and return the column to its original pressure condition? Well, one answer might be to backflush the column. John's going to demonstrate the steps involved as I go through them. Some, but not all, columns can be backflushed. If the column plug is on the inlet frit, you may be able to push liquid backwards through the column and perhaps dislodge or remove some of the particles. Some columns have the same porosity frits on both the top and the bottom. If you have confirmed you can backflush your column, here's what you can do. You take the column, remove it from the system of course, and connect the outlet to the inlet tubing from the pump. Pumping water, acetonitrile, or your mobile phase through the column for a period of time may end up dislodging some or perhaps all the particles that are clogging the inlet. Note that even though you may be able to turn a column around like this for backflushing, it's not always recommended you run the column in this backwards position for an extended period of time. In fact, some columns are made to run in a specific direction. Again, make sure you check your column specification to be sure. For any column that has an arrow facing in one direction, the positive flow direction, I would definitely check the manual or the data sheet that came with the column to see if it can be backflushed. If there's nothing in the manual or data sheet about backflushing, I would call the manufacturer and ask them if the column can be backflushed. The reason why this is so important is the manufacturers put a larger porosity frit on the inlet of the column and a smaller porosity frit on the outlet of the column. If the column can be backflushed, you need to keep a few things in mind. Obviously, you don't want to backflush any of your particles into your detector cell and have them possibly lodged there. Instead, run the inlet end of the column into a beaker to collect the solvent you're using for the backflushing experiment. A couple other things you don't want to do. You don't want to run a very high flow rate, at least initially, because the column will be blocked. And the whole idea is to dislodge particles. So if you want to start out with a fairly low flow rate, and as you see the pressure go down from the particles dislodging from the frit, then you increase the flow rate and flush the remaining particles at a higher flow rate. Note that sometimes particles can get lodged within the porosity of the frit. In other words, deep into the frit, and it's not easy to dislodge them. In that case, you probably won't be able to get the pressure down by this operation. Most likely, the column will have to be discarded and a new column put in your instrument. We try to prevent particulates from getting to your column inlet. Here's a diagram of how we plumb the system to prevent particulates from entering the system. By putting inline filters in your system, these particles will be trapped. There are many zero or low dead volume inline filters available for that purpose. Here's an example of a filter we use in the 1290 Infinity LC. Years ago, when the column inlet frits would plug, we'd tell users to take them apart and change the frit, or even the entire inlet fitting. But nowadays, the packing materials in our microparticulate columns are so efficient that if you remove an inlet fitting, you'll probably end up disturbing the packed bed, and the high efficiency of your column will be destroyed. So nowadays, we do not recommend taking the fitting off and trying to change the plug frit.
Another approach to protect the analytical column is to have a guard column between the injector and the analytical column. The guard column functions in two ways. Number one, it keeps particulates from reaching the head of the analytical column. And number two, it traps undesirable chemical components that could wind up lodging in the packing of the column and possibly cause a pressure buildup. Usually the guard column is of the same type of packing or even the same packing that is in your analytical column. But the guard column is a very short version that is less expensive to replace. There are many types of guard columns, some that are connected with a piece of low volume tubing and some that are integrated with the analytical column. So there's virtually no volume between the two. The basic idea is to use the guard column as a mechanical and chemical filter.
To prevent buildup of contaminants, one can use filtration of buffers, solvents, or sample to remove particulates from reaching the column. A wide variety of filters are available. Syringe filters of varying diameters and varying materials of construction, the mini UniPrep filter that permits filtration in an autosampler vial, individual filter membranes that are placed in a reusable filtration setup, or glass, paper, or ceramic filters, which are used less frequently. When using membrane filters, make sure that the polymeric material is compatible with the mobile phase and sample solvents. Otherwise, you may further contaminate your system or sample by having dissolved material from the filter. Another method of removing particulates from the sample is to use centrifugation. Here, you would place your sample in a centrifuge tube and using a 4,000 RPM centrifuge for about 4 to 5 minutes, this would force most of the particulates to the bottom of the tube. The clear sample solvent above the sediment should be carefully removed to avoid getting particulates back into the solution.
Okay, so filtration aside, let's say you have a clog in your column. What should we do first?
The stainless steel frits at the head of the column are usually inert, at least to most molecules, so they do not usually interact chemically with your sample or your mobile phase. It's mainly a physical type of blockage. But the column packing itself is chemically a very high surface area sorbent, a bonded phase packing that has material that's going to retain chemical substances. That's why, of course, we use them for chromatography.
Unfortunately, some substances are going to be so well retained, especially at the head of the column, that they plug the packing and cause column blockage, and that causes pressure buildup.
So if the blockage is not due to particulates in your frit, it is probably due to chemical contaminants on your packing. Most likely, as stated before, the contaminants are building up on the top side, the inlet side of the packing, because that's where the sample and mobile phase first hits the column. So any materials, be they polymeric materials, high molecular weight materials, proteins, basic compounds that interact strongly with silica, whatever happens to stick tightly to the column, it's all going to happen on the front end. The best way to deal with these contaminants is to find a solvent that will dissolve them without affecting your column. Clearly, you don't want to use such a strong solvent or a basic solvent that's going to dissolve your packing or cause a problem there. So you want to use solvents that are stronger than your mobile phase. First of all, we talked about backflushing earlier. It's really best, if you're going to try to wash the column, and the column can be backflushed, to actually backflush any chemical contaminants from the inlet of the column backwards. The reason we do this is because the contaminants are often on the top of the column, and that's where they're very tenaciously held. In other words, you're not going to be able to move them easily. When you have to pass the chemical contaminants through the entire column length by running it in a forward direction, it may take a very long time and quite a lot of solvent. And your column will be out of operation for quite a while. Whereas if you backflush it, since it's all lodged at the head of the column, this could be a very short distance to remove them. But I'd like to caution you again, only do this backflushing with the columns that can be backflushed.
Ron, one of the most common questions I hear is how much solvent to use to flush through the column for the cleanup process.
Yes. The normal amount we flush through the column is equivalent to what we call a column volume. A column volume is the amount of solvent that it takes to flush all the old solvent out of the column. It's the void volume, or the volume of an unretained compound, to pass through the column. For a typical column that's 15 centimeter long and 4.6 millimeter ID, the column volume would be about 1.5 mils. Here's a way to figure your column volume for a column you're using. Generally, we use 60% as the porosity volume of a packing for Zorbax columns. So you can figure out, if you want to do 10 column volumes, that would be 15 milliliters of solvent. So just to be safe, that's what I would recommend for each stage of our washing experiment. Many of us are using reverse phase chromatography, where the A solvent is usually a buffer salt in water, and the B solvent is a water-miscible organic solvent such as methanol or acetonitrile. When we start to do the backflushing experiment, we want to make sure we don't add organic solvent directly to the buffer system, because if we do that, there's a good chance that the buffer may precipitate out of the column, and that's going to cause even further back pressure problems. So the first thing you do is to wash your column with the mobile phase you're using for your method, but without the buffer salts present. Okay, now we have a column that has water and acetonitrile in it. The next step is to wash the column with 100% organic, again in the backflush mode. Typically, if you're using methanol, you would start with methanol 100%, then move on to a slightly stronger solvent. In this case, acetonitrile would be a good choice. So, you see, as we go to a stronger solvent, the chances of displacing or removing some of the chemical contaminants will go up. If acetonitrile is not strong enough and the pressure does not start to decrease, you may then need an even stronger solvent. When you get past acetonitrile, we start looking at the allotropic series and choose a stronger solvent that might be used. The next solvent I'd recommend would be the addition of isopropyl alcohol, or IPA, to your last solvent that you were using. IPA is a very good solvent for many nonpolar molecules, and it's also miscible with many commonly used solvents like acetonitrile and methanol, but it's also miscible with water. So I'd continue with a mixture of 75% acetonitrile and 25% IPA. Now, as we go along, we want to ensure that the pressure drop is going down. If the pressure goes down after any one of these solvents, that may be sufficient. You don't have to go through the rest of the solvent series.
Wow, this process can be laborious.
Yes, John, it can be. And there are other things you need to be cautious about. When you have mixtures of various solvents with isopropanol, IPA has a very viscous nature to it, and so the pressure is going to be much higher. So you don't want to run a very high flow rate, at least initially, when you start to use this backflushing experiment. If you're running 1 ml a minute normally on your LC, you may want to run backflushing experiments at about 1/4 ml a minute or something like that.
Okay, so now you've done methanol, acetonitrile, and 75% acetonitrile with 25% IPA. What's next?
Well, if that hasn't solved the problem, then I'd convert to 100% IPA. Many times, that series of solvents will take care of the problem. If it's something that's very, very nonpolar that's clogging your column, then there are 2 other solvents that might be used as a last resort. One of them is methylene chloride, and the other one is hexane. So obviously, we'd pass through 10 column volumes of those 2 solvents and see what happens to our pressure. If the pressure still remains high after this whole series of solvents, then probably the column is going to be very, very tough to regenerate.
Okay, walking through this process, it's easy to see why many people just opt to replace their column instead of trying to backflush it.
Yes, or many will use guard columns as a way to prevent this column buildup, as we've discussed earlier. So let's assume we've gotten the column free of chemical contaminants. Now we want to get back to our aqueous mobile phase. What do? Well, we don't want to go right from methylene chloride to hexane to our buffer because they're not miscible. We have to go through an intermediate solvent that's miscible with both organic solvents like hexane and methylene chloride, or aqueous solvents like acetonitrile water or methanol in water. So what we do there is go back to our isopropyl alcohol, because IPA is miscible with all types of solvents. And again, once you get 100% IPA, you can go back to 100% acetonitrile, if that's what you're using, and then go back to your mobile phase without buffer salt, and finally back to your mobile phase with the buffer salt.
Going through all this should definitely be motivation to use guard columns and filters to prevent this as much as possible.
Yes, that's right, John. I'd like to make a point about buffer salts. One of the contaminants that sometimes causes back pressure buildup inside the column is the precipitation of buffer salts. Somebody would have to put a very high concentration of organic solvent with a fairly concentrated buffer, maybe 50 millimolar, to get buffer salt precipitating out. The best way to remove these types of salts that are precipitated out is to run water through the column, because water will dissolve the salt. If you're using normal phase chromatography, you have a slightly different setup. With normal phase, you're strictly using organic solvents. In this case, we recommend a couple of different solvents for washing a normal phase column, such as a bonded cyano column or a silica gel column. Here we recommend to use about 20 column volumes of solvent. And the 2 solvents we recommend you try out if you have a plug packing would be a 50% methanol, 50% chloroform mixture, or 100% ethyl acetates. These 2 solvents might just be enough to do the job.
Okay, let's recap.
First, remember the pressure equation. There are 5 factors that contribute to pressure: column length, radius, particle size, flow rate, and viscosity. So pressure changes are going to be explained by changes in these factors of your method or column that you use.
Increased pressure that is outside of these parameters is likely a result of contamination or blockage, either in your column or your system. And discovering that source of contamination is the goal to get back to robust chromatography.
Start by disconnecting your column and checking the pressure to see if that fixes the issue. If it does, then you know you need to look at your column. You can work upstream through various components, your inline filters, your guard columns, your autosampler, and so on, to see which one makes a difference. That will help you isolate your pressure problem.
Once you have it isolated, there are a number of things you can do to remove the contamination. First, you can simply replace the part.
In addition to particulates, there are dissolved contaminants to consider. These may get onto your column packing. Again, you can backflush your column to address these. Using a guard column will help you lengthen the lifetime of your analytical column. For a buildup of buffer salts, run 100% water through your column. If you're using normal phase chromatography, you'll need to use strictly organic solvents for any column washing.
Try preventive measures to avoid particles entering your system. There are inline filters you can use. There are also sample preparation steps you can take, such as filtration or centrifugation of your sample. You could try using a convenient device like the mini Uniprep filter.
If you tried these steps and still can't solve your issue, contact Agilent's technical support. You can find information for your location at www.agilent.com.